right? So you understand the reason. Ceramics are very brittle. Brittle means that only the straight line linear elastic region is there, though it may be very high, it may go to very high strength, but suddenly it just breaks. So because it does not start the plastic deformation in a very significant manner, therefore there is no yield strength. Composites and fibers. Composites, on the other hand, are materials that we make ourselves, and we either mix a metal to a polymer or we mix a ceramic to a polymer, and therefore because it is more than one material mixed inside it, therefore if it is not very easy to find the yield point, especially if it is a composite of a ceramic and a polymer, and ceramics already do not have yield points, so therefore we do not have yield points for composites also. Ultimate tensile strength. Ultimate tensile strength. You see, just by the name, what do you feel? What do you feel? Tensile strength is a strength under tensile load, right? Ultimate means what? In normal English, ultimate means maximum value. So the name is very clear that if you draw the stress strain diagram, then whatever is the highest point, that point is the ultimate strength of the material, because that is the maximum stress that you can find on the diagram. So it is called ultimate tensile strength. It can be called ultimate strength only, it can be called tensile strength only. So the full name is UTS, ultimate tensile strength, or just tensile strength, or just ultimate strength. That is all the same. You see the words necking there, and true stress and engineering stress, we will explain it when we show you the diagram. We are showing you a typical stress strain diagram for a general standard metal like steels. On the vertical axis is the stress, on the horizontal axis is the strain, and these are the engineering stress and engineering strain, because we are dividing by the original area or the original length. Why do we call it a schematic diagram? Because we are not showing you actual values of a stress or actual values of a strain or actual value of the dimensions of the specimen. So this is a schematic stress strain diagram, but it is a very, very good diagram to give you the typical behavior of a stress strain for any standard metal. In the beginning, in the straight line region, we have the elastic region. Once it crosses here, all this is the plastic region, this you know. Now here, whatever was the original specimen, if it is here, it has elongated, right? The length has increased, the diameter has decreased, the length has increased, but the diameter is still a uniform diameter all through. Of course, if this is in this region and at any time you remove the load, this specimen will go back to the exact original size. Once it passes the elastic region, the yield point, then now it is all in the plastic region. So from here, yield point until this maximum point on the curve, right? The maximum point on the curve is the ultimate tensile strength or the tensile strength, right? So the plastic region is from here till here basically, and then it extends a little. Here, if you see, compare this one to this one, it has further elongated and the diameter has further decreased, isn't it? So the length has increased, the diameter has decreased, but it is all uniformly same diameter still, okay? But now it is plastic. If you remove the load now, then it will be permanently deformed. The length will not go back to the original length. Once it reaches the maximum point here, obviously it means that the maximum stress that could be applied on the material has already been applied. So all the time the material is weakening, right? The material was there, now you have elongated it, you have elongated it further, you have elongated it further, you have elongated it to the maximum point. So length is maximum, diameter is the smallest here, okay? So therefore it is very weak. If now you further load it, then the material has become weak. It cannot resist so much. So now what will happen? It will increase, but now the diameter will not remain uniform. Until here, any point here or here or here. The length has increased, but the diameter is uniform. Now there will be a small diameter here and the rest will be a little larger diameter. So this is like a neck has formed, N-E-C-K, neck. It is just like our neck. You see, the head and face is a bigger size, the shoulder is a bigger size, the neck in between is a smaller size. So this is the neck area. So this is a neck area, and forming of this neck is called necking, right? So once the ultimate stress point is reached and you further load it, then necking starts to happen because the material has become very weak. Now you know that necking means that here there is a smaller diameter. So when it is here, anywhere here, you have a certain force that you have applied. You divide that force by this dia. Then there will be some stress. But you divide the same force by the neck dia, right? The stress will be higher because this value is smaller. So at the neck, the stress is much higher compared to the rest of the piece, rest of the specimen. Therefore, ultimately it will break from here. So once it reaches the fracture point, then the sample breaks, and generally it breaks from the neck. In a bad specimen where the material properties were not uniform, the material was weak somewhere else, then it may break somewhere here also. But if the material is uniform, if the material is homogeneous, then the neck will form and the fracture will be at the neck region. So this is the ultimate tensile point. This is the fracture point. This is bad word. This is fracture strength, not ultimate. Ultimate is a bad word. And this of course is neck. And there is a stress concentration because the area at the neck is smaller. So we have shown you this schematic diagram for the whole spectrum until it breaks. But what we wanted to explain is the relationship of the ultimate strength, which is the highest point on the curve, and that once you pass it, then necking starts to happen, and necking is the reason that the thing actually breaks. So here we are showing you two real diagrams now. This is not a schematic, this is megapascal stress, this is strain values. This is for 2024 aluminum alloy. This is tempered. Tempering is a heat treatment where it gets stronger and harder, and annealing, we will see much later on, is a heat treatment process where it becomes softer. So it is aluminum 2024, this also and this curve also, both curves. But the same material, if it is in the annealed condition, is pretty soft. The same material, if it is in the tempered condition, is pretty hard. So it goes to hardness, high strength, then the ultimate point, and then it fractures. It goes there to the ultimate point and then it fractures. But because it is soft, so there is more deformation before it breaks, right? That will always be the case. If it has become harder, it is stronger, it can take more force. But now it fractures here at this strain. This fractures here at this strain. So it means it has more deformation. So if it is softer, it is more ductile. It can take more plastic deformation before it fractures, and it can take less plastic deformation before it fractures. But the thing is, maximum point. Maximum point is ultimate tensile strength here or here. So therefore, necking happens on the sample, and ultimately the sample breaks, and right, it breaks in the center. Okay, so this is your ultimate tensile strength and the problem of necking